So let's look at the day in the life of a data scientist, traditionally versus the GPU. So if you have a CPU powered workflow, how will it look like, right? So you start with the dataset download. That's your first thing. Obviously, it takes a long time for you to download the dataset. You configure the ETL. ETL stands for extract, transform, and load workflow. So generally, your data would be in a format which is not very, which needs to be transformed. So it needs to be extracted, transformed, and then again loaded. So you start the ETL workflow, but it takes a lot of time. And you can see here most of the time why the data scientist is spent in just waiting for the things to be done. And then suddenly you realize that in your ETL workflow, you forgot to add a feature. Then you again start the ETL workflow. Again, you wait for it. Then after your ETL workflow ends, you suddenly realize that there was unexpected null values which are coming. Then you again restart the workflow again. And by the end of it, you see how much time is actually spent in doing execution. So the red part is the one where the actual action is happening, and rest all part is just waiting. You can see different legends, some for training, some for inferencing, some for analysis, and some for data set collection. Now, what we want to do is we want to move from this left-hand side of the diagram to the right-hand side. So your dataset download obviously cannot be accelerated. You move towards starting your ETL workflow, and you can see that it doesn't take a lot of time to do the extract, transform, load. Then you realize that you have missed a feature. You again start it. You find the unexpected value. You restart the ETL. You train the model. Then you validate the model, test the model, experiment with it, and optimize it and repeat it. So, and you basically even can go home on time. So the idea what we are trying to say here is that our time should not be spent on the data scientists are one of the most critical resources in an organization. And if the time of a data scientist, you can think of something like in a hospital, you would realize that one of the most critical resource in a hospital whose time needs to be saved the most, and that's why most of the healthcare workflow are around this person is the radiologist. Radiologist is the one who looks at all of your images and tags them with the observation that they have after collection of the data. And if you look at the whole healthcare flow, it revolves around making sure that the time of this radiologist is saved. The same logic kind of applies even for the enterprise segment also. One of the most critical resource that you can have for the enterprise segment of our is the data scientists, because data scientists are most critical resources and they're hard to find. And that's why the whole software stack should revolve around making sure that the data scientist time is more optimally used. And we want to move from this left-hand side to the right-hand side diagram with help of rapids. But you need to also understand to a certain extent the history of how this evolvement has happened with respect to data processing. All of us would have read about the big bang of the big data regime, where one of the most popular framework, Hadoop, was built over the MapReduce phenomenon, right? So it was primarily this cycle which existed. So you have your data, it is being spread out across different nodes, different storage, and you have to do Hadoop data file system read. Then you query the system. The query basically meant that you're going to transfer the compute to where the data resides. So the data is spread out, and you basically send your computation towards where data is, and then finally whatever is the result gets accumulated. And then again you have to do the HDFS write, and then you keep on doing HDFS read. You first query it, and then you do your extract, transform, load, then you again do a write, you do a read, and then you actually start your ML training, which is the machine learning training. Now for a user, it kind of changed the industry for a large extent because it solved one of the problems of distributed computing, because the data set was increasing and you used to get tons of data every day and there was no other way to do it. And that's why this map reduce framework kind of solved a lot of challenges. But there was one particular problem with this which needs to be sorted out. And that challenge was this reads and writes which were happening to the file system. Any one of us would be able to tell that reading and writing from disk is the most costly operation which can be done, because that's the one which takes majority of the time. Compute is kind of free, but your memory is kind of or the file reads are the most costly thing which can happen. To solve this problem, there was innovation which was Spark. Spark is basically solve the problem by keeping all of it in memory. So most of the computation, whatever we want to do, comes from the data which is residing in memory. So you can see here, for the first time, there was a HDFS read, but after that, whether you're doing the query, extract, transform, load, or ML train, everything is happening in memory. So your overall pipeline is happening in memory. Because of this innovation, there was almost 100x speed up as compared to the to doing the file reads and writes. There was also necessity to there was also an improvement in terms of writing lesser code, and it was one of the main innovations which resulted into a lot of improvement. The next set of improvement came was that now we have solved the problem of reading it from file, but my query, extract, transform, and load an ML train takes a long amount of time, which is the compute part of it also. So in order to solve that problem, as GPUs were becoming more and more popular, deep learning also was becoming more popular. There were innovations done in terms of making sure the query, ETL, and ML train pipeline is also put on the GPU. So you can see here, rather than doing a normal query, ETL or ML train, so you do a HDFS read, which means you read from the file system, but then after that transfer that data to the GPU using the GPU read functionality. Then the query takes a very short amount of time, because now you can accelerate it using different cores on the GPU. Later on, you have to again do the transfer to the CPU, not to the file system, but to the CPU, because of because there were certain pieces which are missing. So again, you need to go back to the CPU. CPU will do certain amount of work. Again, it was given to the GPU for the extract, transform, load. Again, write it to the CPU RAM, read it from GPU, and finish the ML train. Now, with the innovation of the GPU processing, you could result into reducing the time for calculation of your query, extract, transform, load, and ML training. But there was still a problem, which was reading and writing to the CPU, reading to GPU and writing to the CPU. Hence, the improvement, which could have been much many folds more, basically was only 5 to 10x. But then, because I had to read and write into memory again and again, I had to increase my source code, and it became too language rigid, because I had to use certain specific language to read or write code on the GPU, and a large portion of it was then doing these transfers rather than actually doing the computation. So yes, there was a 5 to 10x speed up in this overall pipeline, but there were certain additional overheads also which came. To solve that problem at that time, there were not all the right set of pieces, and that's why we had to do all of this. Then came a project which is called as Apache Arrow. Apache Arrow was an innovation which kind of solved one big problem which was existing in this data science space. There are so many frameworks out there, and each and every framework has its own way of talking or reading or writing or interfaces. Apache Spark, Pandas, Impala, HBase, Cassandra, all of them, basically each system had its own internal memory format. And generally, one framework is not enough in an enterprise segment. You need to provide data from one to the other. And hence, whenever you had to do that interface between different frameworks, you had to do serialization and deserialization. So you had to convert up, like from Spark, if I were to send to Pandas or if I were to send to Drill, I will first do the serialization, and again when it comes to Drill, I will do deserialization. So 70 to 80% of the time was wasted in this conversion from one framework to the other. Apache Arrow kind of solved this problem because it exposed all of them with the same memory format. There was no need for any kind of cross-system communication, and the project basically can share the functionality as well. And with this innovation, all of the missing pieces to make the overall thing run on the GPU were kind of present. And that's when the goal that we had in mind came. So instead of doing a HDFS read, now the whole thing sits over Apache Arrow. So what we do is we read it from Apache Arrow, and then after that there is no read or write happening through the CPU. Everything remains on the GPU, and once you have done or everything is in Apache Arrow, then you do your query, extract, transform, and load, and ML train all of them on the GPU itself. Now that's where a lot of innovations came into the picture, and you can see here how many folds increase. This is the cycle of the data science. First, moving from file system to in-memory system, giving you 100x speed up. Further moving towards using GPU, giving you 10x speed up, which is like 1000x speed up from the top. Then again more 100x speed up by making use of Apache Arrow, which is almost like 10,000x speed up by the innovations with respect to changing the pipeline and using the right set of tools and technology. And that is what is the necessity of the hour. So as I said, why Rapids is kind of visible. You can see here one of the example from H2O.ai machine learning framework. And you can see the CPU and the GPU, which is kind of listed. These are kind of old GPUs and CPUs. Both of them are old. They are 3 generation old. But you can see here on the GPU side, the models trained and evaluated because you need to try out different combinations, different type of parameterization. The GPU is already doing the validation for all the different types of parameters, but the CPU is yet to even start giving out results. And this is for the US census data, which has 45K rows, 10K columns. And for validation, we are using 5-fold cross. So in fact, we have got one of the results here. You can see here now is when it has actually started doing something, while the GPU has already finished all the parameters. So the big problem in data science, again, it comes to the part of what is the cycle in this data science community. The first part is managing the data itself. So you have your data, you need to do the extract, transform, and load part of it, and you store it in form of structured data store, which is then provided to the training phase, where you again prepare the data, you do the model training, you have to evaluate it using some visualization tool, and this is kind of a cycle. The cycle is to keep on doing this, and then finally you deploy it also. So Rapids is basically an end-to-end data science pipeline which is completely in GPU. So it helps to make your ETL pipeline, the data preparation, model training, and visualization, and to certain extent even your deployment ready and accelerated on the GPUs. And one of the best thing which we talked about Rapids also is it looks very similar, and the feel is very similar to what a data scientist would have traditionally used when GPUs were not existent, and it will look very similar to how the APIs were in the CPU world. So this is an example of the healthcare data science where you have data. The data basically comes from different devices. You have different sets of medical records, claims, variables, medical devices like MRI machine, CT machine and all. You have to convert all of this. You have to extract it, transform, and then finally load it into something called as a data lake. Once the data is in the data lake, you need to basically you need to prepare the data for training. So you would do feature engineering, and also you would try to do some in form of data frames. You would manipulate the data, like you will maybe consolidate some of the columns. You may average some of the columns. So there are different sets of feature engineering and manipulation that will be done. Finally, it is provided to your training. So you will apply different types of models here and evaluate finally which is the one which gives you right thing. You will also do cross validation and hyperparameter tuning here to see that you are able to get the right thing. In the process, you might realize that the features that you're using might not be correct or they need to be changed, and it again goes back to your data preparation stage, and it is like a cycle which keeps on happening. And these two domains is typically the pain point for the data scientist. And finally, yes, you have to also deploy it once that cycle is over. So in the Rapids world, you are going to start seeing now certain terminologies or certain names which we are going to introduce you. In fact, each one of them that you are seeing here is going to be one lecture that we are going to cover in this series for the data science or data analytics. We have a library or a module inside Rapids which is called as OPENUCX, which is responsible for taking it from the data lake. And then for the data manipulation of feature engineering, you're going to use something called as ODF. And then for the training and evaluation, you will use a module inside Rapids called as OML. The name COO here comes from the fact that it is accelerated on the GPU, and all of the libraries on the GPUs or the architecture of the GPU is called as CUDA, which stands for Compute Unified Device Architecture. That's why the libraries are tagged or are in the beginning with the name COO, which is primarily coming from the CUDA side of it. So the Rapids library, there are different modules which are present inside it, and each and every module is responsible for their own task. So as I said, ODF is basically responsible for the data preparation. You can see here as an example, there is a patient and the patient is having certain features attached to them, date of birth and everything, blood type and all. And then there is another column which is kind of also having the medication there. So you will have each and every patient having different sets of medicine that they would have taken over time, or there are certain observations which have been happening based on the test results which are there. So what you're trying to do here is to combine all of this into one big data frame. Like join, we are trying to do basically in the data base community world, the name here is join. So what you're trying to do is you're trying to join on the patient ID and also try to do group by, and you may also end up doing certain operation during that group by, like doing an average over the last 5 readings, and that's what finally you will get a combined data frame, right? So you have the patient here, so you have combined the part of this particular database and at the same time taken certain observations from here, but also you have done certain averaging based on say the 5 readings. So this is like a data preparation that needs to be done before even providing or provided to the machine learning for the training part of it. before even you go there, so one thing as I told you about Rapids is that it is basically available on GitHub. The source code is available on GitHub. It is present in form of availability via different kinds of platforms. You can install it via Python package like pip. You can do installation using Conda. You can also use Docker, or you can download it in form of a container from NVIDIA GPU Cloud, or you can directly take it from GitHub. And you can run it on any system, including cloud as well as on-premise. From a Rapids point of view, again, it's an open GPU data science platform. And this is where you see there are different parts of the overall Rapids stack. So the bottom is Apache Arrow, as we talked about. And there are different components that we'll go through briefly. And we are going to take certain of these components as one lecture each in the next couple of days of this training. So the first one here that you are seeing is the visualization library itself. There's a slight correction here that the visualization library is not coming soon, but it already exists. The idea behind the visualization library is to do the analysis in the end, right? So it is going to be based on, it is based on Apache Arrow, and it is primarily used for visualizing the data which is coming out of model training, so that you are sure that whatever the model has learned is as per the expectation. It helps you in the validation part of it. As I said, the one of the most critical piece in the overall Rapids which was required was Apache Arrow. Apache Arrow is basically a columnar in-memory data structure. It's one of the most, the two critical word there is, it's columnar, which means it is structured data. As we had said earlier, deep learning is for unstructured data. This is for structured data. It provides in-memory support, and it helps in doing data interchange between different frameworks. And that's why it also supports more complex data models. Then we have something called as DASK. DASK is a distributed computing project which was launched some time back. It has Python interface. One of the most critical thing is that in this world, Python is the most popular language. So it has a Python interface. It is modular in nature, and also the infrastructure. It scales pretty well with different kinds of infrastructure like Kubernetes and also Yarn clusters. So Rapids also makes use of DASK. DASK is not a project by Rapids, but it's an open source project, and Rapids extends it to do the same job on the GPU. So again, why DASK? One of the critical thing about DASK is that it is easy to migrate. It looks very similar to NumPy. So it's built on top of NumPy and Pandas and sklearn. So it's very easy. It's very, because it uses almost the same API, you can use it pretty well. And again, it is supported by the developer community. It's open source. And as I said, one of the critical thing about DASK is to scale it across different nodes with using Python APIs. So it supports all different types of HPC and cloud and other kinds of mechanisms to go across nodes. Like if you are a high performance computing user, if you have a high performance computing cluster, you would use schedulers like Slurm, PBS and all. So it kind of supports the same. If you're in a cloud environment, you would use Kubernetes is the most popular framework for data orchestration that we have seen previously. So it kind of supports that. It's very easy to install. You can install it on your laptop, or it can scale to thousands of nodes as well. And as I said, since it is Python based, it is kind of also very easily used. Otherwise, you had to use other kinds of things like R programming and all, which was not so easy for many of the data scientists. So Rapids, again, let's move ahead with from the DASK. Now we move towards ODF. ODF is a data manipulation library, which we just saw some time back with an example. And it is actually a C++ library, but having Python bindings, and it is used for manipulation of your structured data. So the backbone of data science, as we said some time back, is ODF. We are going to go into more details of CUDF in the next section, but it is a Python library. It is actually having a Python interface for the CUDA C++ library behind the scenes. It has the interface very similar to your CPU side of the world, and it supports high performance using JIT based compilations also if required, using module called as Numba. So again, this is a very a repetition of what we said, but it's kind of clear with respect to what QDF is used for. Once you are done with the data manipulation, that's where you move towards the next one, which is QML. QML, as the name says, it's CUDA accelerated machine learning. It is a collection of GPU accelerated machine learning libraries. And it provides the equivalence to something called as sklearn or scikit-learn, which is very popular, and almost all the data scientists or everyone who is working on machine learning uses sklearn. So sklearn is a CPU equivalent, while the GPU, if you want to accelerate and run on the GPU, it is provided by Rapids in form of a package called as QML. So as I said, it has almost all the functionalities of sklearn. It provides you time series based options. It has clustering algorithms. It has classification and regression algorithms, and day in, there are many more which are basically coming into this QML. And since it's open source initiatives, there are a lot of algorithms which are getting added. It still doesn't have all the features of sklearn, but it is becoming more and more comprehensive each and every day. So this is just a very short example. If you were to doing CPU based clustering, you will obviously use sklearn, and you would do it in form of a pandas data frame. So you will first create a pandas data frame, then you will import a sklearn clustering algorithm like dpscan. You will do a fit and then a predict. Same thing on a GPU, you can see practically there is only two change. One is, instead of importing sklearn, you are basically, instead of importing pandas, you are importing QDF, and instead of importing sklearn, you are importing QML, and rest of your code remains the same. So if you have a GPU, just by changing or importing, you can actually get the kind of performance that we were talking about some time back. QGraph is a framework, and it is basically a connection of graph analytics library. So many of us want to work on graph algorithms. So there is a package which is primarily responsible for doing only graph related activities. So here are again certain additional benchmarks, like if using QIO and QDF. So if you were to do the data frame manipulations, how many CPU nodes? So everything is kind of listed here, what database, data set it is, what configuration is being used and all. So it takes so many amount of time, but on a one DGX system, which is a DGX with 16 GPUs, you can see still 100 CPU nodes is not able to meet the same speed that we are expecting. Same goes with QML. Even with 100 CPU nodes for this algorithm called as XGBoost, one GPU node is still surpassing by different folds a combination of 100 different CPU nodes connected to each other. And if I talk about the whole end-to-end pipeline, again, you can see one GPU node is surpassing 100 CPU nodes by many folds. And that is the part that I had brought out in the beginning, which is return on investment. The return on investment is very critical to making data science go in the production environment, and GPU kind of, or accelerated data science with the help of GPUs can actually solve that particular problem as well. It's not just about acceleration or reducing time, but also getting your return on investment with respect to the never ending increasing workload. So as I said, Rapids is basically an open source project. You can anytime go to github.com/rapidsai and you can basically download it, or you can, in fact, in case you're facing any problem, you can report a new issue, report a problem, or you can in fact raise a feature request which you want, which is not there in your current data science pipeline. If I were to summarize whatever I talked about, this is the open source data science platform which is familiar to all the CPU or the sequential computing environment. So for data preparation, you would generally use the most popular library out there is Pandas, which is used for analytics. And then for machine learning, you have sklearn or scikit-learn, which is the most popular machine learning framework. And if you want to take it across different nodes or distribute it, you have DASK. For graph analytics, you have the most popular library called as NetworkX. And then for deep learning, we have seen, and for visualization, you will typically use matplotlib or seaborn. Now, the same equivalent in the Rapids ecosystem would look something like this, where instead of pandas for analytics, you end up using QDF or QIO. Instead of using the sklearn, you just change the imports to using QML for machine learning. Instead of using NetworkX, you can use a library called as QGraph for graph analytics. We have already covered the deep learning part in Extreme, but for visualization also we have a library QXFilter and PyVis, which kind of accelerates not just visualization of small data, but the large amount of data as well. But also to support the overall pipeline in memory and to have the compatibility across different frameworks, everything is done over Apache Arrow so that it remains also in the GPU memory. So if I were to say, with respect to scaling, the traditional environment of PyData, which is NumPy, Pandas, Scikit-learn, NumPy and all, you can scale up or accelerate by using Rapids framework like PyPy, QDF and all. But you can scale out across different nodes with help of DASK as well. So you can scale by using traditional DASK, or you can scale using Rapids plus DASK, which kind of supports multi-GPU, multi-node kind of an environment as well. So today, what we have seen is a very quick introduction on the motivation towards accelerated data analytics or data science. We talked about different kinds of roles: data scientists, data engineers, the cycle, the pipeline through which the overall cycle goes, which is the data preparation followed by the training and finally the validation and also deployment. We talked about a framework or the package which is called as Rapids, which helps in accelerating all of this, and different components of the Rapids package. And we are going to look in the next couple of lectures into more detail of each one of them in form of a demo session.